Thank you, Matteo, and all the CLIC members for the opportunity. I'm Silvia Cassino, I'm a PhD student at in Subra University under the supervision of Alessia Aldevi. And today I'm going to present part of my PhD work that was also developed in collaboration with the group of Marco Marangoni in the University of Lecco. And today I'm going to talk about the up-conversion photon number resolving detector we tried to develop and characterize in our lab. So first of all, why? For those of you who know Alessia and Maria Bondani's group, they know that they have quite a long history with photon number resolving detector. And to my knowledge, they started with hybrid detectors, hybrid photon detectors. And it hurts to say how many years ago, but I was already around there when they switched to silicon photomultipliers detector and started the characterization of this detector and the acquisition chain to make them suitable for quantum optics measurement. So when we saw that there were some theoretical works about photon number resolving detector used to perform quantum communication, and also some experimental work, the question became, why not? And we started to characterize what we call a homodyne-like detector, which is basically similar to homodyne detector, but with photon number resolving detector instead of photodiodes. And here is the paper we published about that. So why silicon photomultipliers? And then we will come to why the up-conversion. Silicon photomultipliers are compact objects. They work at room temperature and they operate at low voltage. So actually from an energetical point of view, they might be of interest. They have a high photon number capability, and their quantum efficiency goes up to 60%, which is quite good for room temperature devices. But they have a sensitivity in the visible range. And this is why we come to up-conversion, because typical fiber communication works in the C-band, so infrared, but it's well known that silicon and infrared are not really best friends. So this is why we managed to work with up-conversion. So first of all, let's have a look at the acquisition chain. So our detectors are supplied and amplified by the PSAO unit from CAEM. The amplifier is a fast one, and we typically work within 17 dBs. Okay. And we acquire using an analogical integrator with a gate of about 10 nanoseconds, or the acquisition chain was developed to reduce all the drawbacks that typically characterize silicon photomultipliers. In particular, we experimentally measured that the dark counts in this case is reduced to 0.3%, and mainly this is due to the fact that we were triggered to the laser source. So first of all, the first characterization we performed of this detector was in visible light, more specifically green light. But as I mentioned, we wanted to test their suitability for real C-band communication. But we had no infrared source, I mean, not for communication. So we had to build one. Our laser is a ferrous laser, Italian laser, so with the fundamental at 10-30 nanometers, and it's a femtosecond laser, less than 200 femtosecond per pulse, and we operated it at 3 kilohertz. The repetition rate is bonded by the acquisition chain that could be improved. So first of all, as I say, we need to generate our 50 nanometers pulse. And so to do this, we first of all generate white light continuum. Okay. Okay, so first.
Quello centrale.
Okay, so first of all, we have a first part where we generate white light continuum with, using a 1 centimeter YAG crystal. And then this we amplify with an OPA, with single pass OPA, the 50 nanometer wavelength with the second harmonic. So here we have the OPA. And then in the first configuration I'm showing, we generate, so here we generate the beam we want to manipulate, the 15 nanometer C-band beam. And then here we convert it to a frequency that can be seen by our detectors. So in this case, it's a 620 nanometers, a red beam. In this first configuration, we generated the red beam by the sum frequency of the generated beam and the residual pump, so the 130 nanometers. Okay, so here are some spectra just to give an overview. The first, no. Okay, see. Not that. Okay. So the first one is the visible and the infrared region of the generated twin beam, the generated white light. They were taken with two different spectrometers, so they're not really comparable in the intensities. And here we see the amplified 50 nanometers, and here we have the generated up-converted beam, the one that we are going to measure. So this is the one we are going to manipulate, and this is the one we're going to measure. So first of all, so it's known that white light continuum is a threshold phenomenon. So we managed to generate it by being over threshold. But when we try to measure, our protocol is based on coherent state. And when we try to measure our generated state, we try to characterize their coherence. And we found out that they were not coherent, meaning that they show quite intense fluctuations. So here we perform a measurement of the coherence, let's say, by changing the pump energy of the white light continuum. And here, so we first of all reconstruct the probability distribution of the photons to see that it becomes more and more Poissonian as we increase the power. And as well from the auto and cross correlation, we show that there is a behavior that approaches the expected value for the Poissonian light. And in particular here, we report the two functions we used expressed in terms of detected photons. So we find out that we need to stay at the power that was 6 times the critical power we expected. But then we set that, and so we wanted to compare our generated beam with a well-known Poissonian beam. So we chose the second harmonic, the built-in second harmonic of our laser, and we compared both the distribution and as well the auto and cross correlation, and we were quite satisfied with what we were able to generate. So we decided that it was time to start manipulating our beam. Before doing this, we changed a little bit our setup so that we could reach a higher intensity of the laser beam. So instead of generating the red beam with the residual pump of the OPA, we decided to have still a collinear, quasi-collinear interaction, but with a portion of the laser pump, of the laser fundamental wavelength, so that we could reach higher intensity for the red beam. So first manipulation we performed was why not malus law. So we used a polarizer to change the intensity of light. We try to reconstruct the behavior. So here we okay. So here we can observe the behavior of the 1550 nanometers that was acquired with the spectrometer. And here we have the behavior of the 620 nanometer, 620 nanometer. At the beginning, we noticed that there was some something that reminded of a phase mismatch in the linear interaction. We didn't understand why, and until we looked at the extinction ratio of our polarizer, that was quite disappointing. And so, okay, we had an explanation for this behavior. And finally, we decide to perform a fancier manipulation. In particular, we decide to study an amplitude modulation, so the coexistence of different mean value, different coherent state with different mean values. In particular, we studied in terms of correlation, of expected correlation, that here are expressed as a function of the Fano factor. That's just the ratio between the variance and mean value. So we performed two different modulations. In the first case, we chose two mean values and we changed the prior probability of each one of them. And the second case, we chose different mean values, like 2, 4, 6, and 8, different mean values, and we fixed the prior probability. So, yeah. Okay. So here are the two Poissonian states we are mixing, and here we can observe the reconstructed probability, the reconstructed photon number probability, as a function of the prior probability of one of the states. So one minus the other is the second one. And in terms of correlation, we are quite happy with the result, meaning that the measured correlation corresponds to the theoretical one. In the second case, when we fix the prior probability and we mix more states, there is some, let's say, not correspondence with the theory. We try to understand why, and according to our results, this and some simulation we made, this is due to the fact that the states we chose to modulate are not equally separate in mean value. So this leads to some mismatch between the theoretical and the measured result. But still, we are quite happy with the result we obtained. So, of course, there is a lot of space to improve this setup, but these first results are quite promising to us. So thank you for your attention.